I'll just give it a couple more minutes before we get going to give chance for people to arrive. Okay, I think we'll start now. So welcome everyone. This is a session showcasing some of the latest research going on in the CESI programme. And just to highlight to you all that the session is being recorded, so just to let you know that. We've got three sessions being presented, three presentations here from David Jenkins at Heriot-Watt University, who's going to present to you on some work undertaken, bringing in some more societal aspects into technical community energy modelling. We've then got Akil Joseph from Newcastle University, who's going to look at liberalised energy markets from a game theory-based approach. And we've got Mansouri Zanjiabadi from Newcastle University, who's looking at smart mobility solutions. So please do put your questions in the chat, and we will make sure we'll allow some time for that at the end of the three presentations. So to kick us off then with the three, Dave, do you want to present your research on socio-technical energy modelling?
Okay, thanks very much, Claire. Hopefully you can all see and hear me okay. So, yeah, so this project was a CESI Flex Fund from last year, where we were trying to understand how to model decarbonised heat for low carbon communities. The kind of starting point for the work was understanding, first of all, that we needed to wanted to apply energy models at scale to the built environment. That's, you know, a continuing theme of CESI is how you do these things at scale, particularly if you're focusing on buildings, to move from the individual to the at least the community scale. And what's important for those communities when you're trying to design low carbon pathways. So whether you're a local authority or a technology service that's servicing that community, how do you design for a low carbon pathway? And in terms of the models that we currently use, what can they do? What do they currently do quite well? What could they do better? And what are they not supposed to do in the first place? So those are the kind of sort of starting point for these questions. But we want to do it in a genuinely multidisciplinary way. So we weren't just focusing on kind of kilowatts and numbers going into models. We were trying to think about the wider setting of those models and the wider use of those models. So we had myself, Andrew Peacock, Peter McCollum, and Vivi Batugiu from Heriot-Watt, and Claire Copeland and Gordon McCarran from Sussex. So I'll go through the steps that we carried out in a minute. Just a bit of background to modelling more generally, particularly with energy and building models. So purely technical barriers are quite well documented. So the limitations of the physical engines of models are quite well discussed, because you can just open the bonnet of the model, you can see the equations and the science behind those models. That you can actually document those quite well. But there are other issues exist that are more difficult to summarize. So again, a common theme in CESI is this qual-quant communication. So the idea that we're using models that are set up to use very numerical quantitative data, but we might have something going on in the community that's described quite well in a sort of qualitative or discursive kind of way, that might have an impact on energy behavior or energy purchasing or the likelihood of a low carbon scenario being met. But there's not an obvious way of channeling that information from that description into something that ultimately results in inputs into a model, numerical inputs into a model. So there's this barrier that we've discussed a lot within CESI. There's also this tendency for the kind of models we use to think about homes in terms of average or typical households. So if you look at stock modeling approaches, whether that's looking at an entire country or just a region or a community, is this desire to categorize buildings in a sort of neat and tidy way. But of course, the way we use energy in buildings isn't always that neat and tidy. So by moving towards an average or typical household, it becomes more difficult for you to tailor a model to very specific issues that might be affecting a community. And then there's the issue of data availability. So first of all, does the data you need, does it exist at all? Is it measured? Is it recorded in some usable way? But even if it is recorded, is it accessible? Because for reasons of data protection, you might not be able to get easy access to that information in a way that you can actually use it within some of this kind of modeling environment. So the project approach was, first of all, to define the scope of the modeling we're talking about, because energy modeling, even building modeling, can mean 5 different things to 5 different people. So we wanted to define what we actually meant by modeling, and we were using our own energy model as an example of the kind of thing we were trying to do. We then ran a stakeholder interview stage, which was carried out by Claire, looking at the perceptions of the challenge. So that's trying to understand from, in particular, users of model output, what they perceive as being the challenge to a low carbon future. What are the kind of hierarchy of issues that they have to deal with when looking to use the outputs of models. We pulled some of that together to create kind of conversation topics, a sort of structured conversation that we could then have within the third stage, which was a workshop that we ran, looking at the suitability of models to address key issues. So how fit are these models to actually address the challenges that are being identified? And then we had a sort of final stage where we looked at our own community energy model and thought about to what extent are we able to actually encapsulate some of these key issues that are being put forward, or to what extent should we be trying to do that in a model of this type. This particular example, which I spoke about a little bit yesterday, and we've got posters in CESI which are describing the model in more detail, but the idea is that we can pinpoint a community. This one happens to be in Orkney. We've also run it for areas of north of Tyne as well. And indeed, outside the UK, we've done some work in India where we tried to carry out a similar process. But the point is that wherever that community might be, how can you point your energy model towards that community and pick up the key criteria of that community, the key input parameters that define that community, which go beyond just identifying shapes and form and systems. So the interviews themselves, we had 10 interviews with 10 semi-structured interviews with a number of key stakeholders, generally non-academics for the interviews, but a little bit of a mix of an audience. But all of these people, I think, were all interested in the outputs of the models. Some of them may have had some understanding of how the modeling environment works as well, but they were particularly interested in the outputs of those models. And that helped us to find key sub-themes that we then wanted to consider in the workshop, where we had 32 attendees, a fairly mixed audience, some from industry, some from academia, some were modelers, some weren't modelers, some we had particularly good input from sort of local authority, local council type stakeholders as well within that workshop. And we carried out a scoring exercise for what modelers or those using models find important. And how would we accommodate these sub-themes that we've identified previously into the modeling? And to start to kind of kick off that discussion, we were asking participants, what data do you need to find out the thing that you want to find out? Who has this data, and what is the reliability of that data? So reliable in terms of how it's stored and the sort of practical side, but also just, is that data reliable in characterizing the thing that you're trying to characterize? So you can see here in this table that we used in the workshop, first of all, we identified 5 broad themes, which are very much overlapping. But this is a kind of a codifying exercise from the interviews, where we identified 5 broad themes that were coming out. So occupants and inequality, so a bit more about what the householders themselves are doing and who they are. Another sub-theme, another theme on buildings, the kind of bricks and mortar, if you like. Energy systems, so the kind of wider setting of these buildings within energy networks and what that might mean and the interaction with that energy system. Issues of governance and the sort of policies and externalities that are affecting the things that we might do as modelers. And then practical obstacles like sort of funding challenges and so on, and whether the carbon targets are well structured, well staggered for meeting, for getting to the place that we want to go to in terms of carbon saving. So those are our 5 overarching themes. And then within those themes, we had these sub-themes, which again were brought out of the interviews that we ran as useful talking points that we could then bring into this workshop. And to get the process going, we asked the participants of the workshop to just score between 1 and 5, 1 being not important, 5 being very important. How important were these sub-themes within your kind of day-to-day interaction with models? So for example, if you look at 1.1 in that list, right at the top, accounting for fuel poor households, those from industry saw that as less immediately important for their interaction with models, as opposed to, unsurprisingly, local authorities and housing associations that have to quite directly interact with this problem of fuel poverty. And this was all before the current jumping in energy price. So this was already a prime concern amongst some stakeholders. So this was a slightly subjective exercise in terms of just putting a number next to something to identify its importance, but it just allowed us to start a conversation around specific issues within this wider modelling challenge that we were trying to discuss. And it's interesting as well, looking at how the opinion of the importance of these sub-themes changes across the different sectors. So if you start touching on things that are more directly relating to markets, for example, 1.3, which was looking at the impact of capital availability and willingness on the uptake of energy efficiency measures, that's clearly about what is the market for different technologies. And so perhaps unsurprisingly, industry found that industry participants in this workshop found that of more importance than perhaps some other factors. So it's just bringing together that diversity of different model users and the different priorities they might have. And then the second activity, which was perhaps a bit more tangible, we asked the groups to think about the relative impact of each subtopic. So that big list of subtopics I just had up on the previous slide. Think about the relative impact of each of those on the modeling that you either do or the modeling that you use, so the outputs that you use. So on that y-axis, first of all, we asked, how straightforward is it for you to quantify that issue? So is the data kind of there? Is it a fairly simple, straightforward set of parameters that you can easily source? Or is it actually something that is as with the kind of qual-quant barrier that I mentioned earlier, is it something that's very, very difficult to quantify, either because the data doesn't exist, or it's not something that's sort of naturally suitable to summarizing it within a couple of numbers? And again, the issue of fuel poverty came out here as something that was quite difficult to quantify. And then along the x-axis, what's the relative impact, or what do you perceive to be the relative impact of that subtopic on the model output that you use? Do you think it's important or unimportant for the kind of things that you're doing with that model? So in the top right quadrant of that diagram, you've got things that generally we're able to quantify them, we feel, and they're also quite important. So we're glad that we can quantify them because they need to be part of our models. In the bottom right-hand quadrant, these are the sort of problem items because they're perceived as being quite important to different model users, but they're actually very difficult to quantify. So we might suggest or expect that our models maybe don't do such a good job at covering some of these issues. And accounting for fuel poverty, which you can probably see in that bottom right quadrant, that's quite a common issue because it's actually a very difficult thing to quantify. Intuitively, we might feel we all understand it. It's households that are struggling to pay their energy bills. But in terms of being able to quantify that and put it into a numerical model, or to even obtain information from that model in a numerical way that can actually talk to some local definition of fuel poverty, because we're applying this to a community, not an entire country, that's actually quite difficult with most fuel poverty metrics. And also the fuel poverty metric changes as you go about the country. It's not the same in Scotland as it is in England and Wales. It's not the same 5 years ago as to what it is now. So that's becomes quite a sort of vague, hazy thing to try to quantify within these models. So quite a good example of things that models should do better. But all those items in the bottom right hand quadrant gives us a bit of a clue as to what we should be doing with our models as we move forward. So just to summarize the findings of all that work, it is difficult to capture the diversity of models, modelers, and different beneficiaries of those models within a small project. And obviously we had to keep numbers fairly small and manageable, both in the interviews and the workshop. But it's just noting the fact that different people want different things from models. But also as modelers, we might be using different models, but we might have different requirements of our models. But we do want a community energy model to address this kind of diversity of use and diversity of application, or at least be specific about who they're useful to. And I think that's a key point for all modelers. As we disseminate the results of our models, we might understand the scope and limitations, but we need to include that description of scope within the outputs that we produce, so that these outputs are not misused by different end users. So application is key. What are these models being used for? And any kind of simplification of input can be justified or not based on our understanding of application. If we overly simplify an input parameter, I'll use the example of fuel poverty again. If we overly simplify that, but then use this output to somehow define fuel poverty or solve or target fuel poverty, then clearly that's not the way to go about addressing that problem. And there were particular concerns, so in terms of things that appeared in the bottom right-hand quadrant of that graph that was seen to be important, but also difficult. There's particular concerns around future scenario modeling. So we have lots of different sources for future scenarios that we might use when we're trying to understand where our carbon emissions might go. But if you're, for example, a local authority or housing association, and you've got a housing stock that you're trying to do something with, you're trying to meet some kind of low carbon target that's being placed on you, then if you're doing that over a long period of time, you want some kind of consistent advice as to other externalities that you might need to bring in, things that you don't necessarily have control of, like obviously climate change, but also technology subsidies, what new markets are gonna kick in, what's the price of those technologies likely to be over the next 10 years, so you can understand the likely penetration of that technology within your particular building stock. So all these issues, kind of trying to sort of standardize those issues so that we can have consistent future scenarios was identified as something that's maybe we need to do more work on. Vulnerable household identification, again linked to the fuel poverty issue, but these type of models don't do particularly well at kind of quantifying the behavior of, or even qualifying the behavior of certain types of households, if you kind of veer away from this typical or average household that models like to use. And then there's the designing and tailoring retrofits at scale. So not just having a before and after scenario, but how can you actually use these kind of models to plan over a kind of staggered timeline where you can target certain types of houses first with certain types of technologies, and then plan a rollout over a certain period of time, a sort of dynamic planning model, if you like. So that was also identified as something that's perhaps missing in the sort of decision support chain that these models could and should provide. And I shall finish there. Happy to take any questions towards the end of this session. Thank you very much.
Thank you very much there, Dave. And as Dave was mentioning there is the opportunity to see this work in the poster presentation tomorrow as well. So moving on to our second speaker, which is Akhil Joseph. You want to introduce yourself and share your presentation?
Yes. I hope it's visible now. Great. So today's presentation is about a recent work, or the work which is being done right now. It's a development of a game theoretic approach for the liberalized energy market of Great Britain for the future investments in the sector, as well as its current operations. Myself, Akhil Joseph, I'm a research associate at Newcastle University, and this work is being done in collaboration with Dr. Adib and Prof. Sarawakar. The current energy system of Great Britain is moving towards achieving a net zero carbon emission target by 2050. And towards achieving this target, there are various factors that influence the targets, which are generation technologies, energy conversion technologies, storage devices, and associated regulations and policies. So in this work, we aim to investigate long-term investment strategies and the short-term operations of the energy system. So the long-term investments are decided based on the short-term operations of the system. So we focus to analyze the impact of investments in renewable energy generation, hydrogen, and vector coupling storages based on few objectives or few focus criterions, mainly to maximize the social welfare and to minimize the carbon emissions. So what we propose here is the game theoretic model of the liberalized energy market to simulate the annual investment. And we also simulate the hourly operation of the model to capture the value of hydrogen and the coupling storages. To achieve this objectives, we have formulated 3 specific objectives. The first one is to demonstrate a game theoretic model of the integrated energy networks, what we have right now at Great Britain. For this, what we have formulated is a Carnot oligopoly competition model. And the short-term operation for this objective is formulated using the optimal power and gas flow model. The second objective is to simulate the energy sector's evolution until 2050 with various configuration of storages. That means with storages and without storages. For this, what we have done is we have formulated scenarios based on published data, which I'll be discussing later. And the third objective is to simulate the investment behavior into the large-scale vector coupling storages to quantify its benefits. So that is mathematically being done by calculating the social welfare of various investments. So to model the long-term investment, what we have done is we have proposed a Carnot oligopoly model, which is a perfect competition model. So the game here is the generators can potentially invest in future in the expansion for the expansion of the capacities while producing energy at real time. That means generators simultaneously decide on their hourly operation and their long-term investments. In the case of a storage investor, they also plan for their storage charging and discharge cycles and their future investments as well. So for this, to simulate this game, what we have done is we have formulated an objective function to maximize the net present value of the system based on the net profit from the system by the players and the initial investment outlay. So the mathematical model will be discussed later. However, right now in this slide, we can look into the interaction between various components in the energy system. That means for an electricity network, we have electrolyzers which use electricity to convert or produce hydrogen, and the hydrogen stored will be later used or converted back into electricity using fuel cell. Similarly, CCGTs use the gas to produce electricity. So our idea is to make use of this interaction into the network. In our mathematical model, we have few inputs. For the annual investment model, we use the base year price levelized costs of various technologies, capacities and capital expenditure, etc. And for hourly operational model, we use the optimal power flow and gas flow model. So for that, we need specific network topology, network parameters, etc. And we have the output is given here. So based on so the output of this mathematical model is the annual electricity, gas, and hydrogen generation, the storage utilization, the social welfare, and the price projections. So we have the input, we have the output. What happens in the middle is the annual investment and our operational model. So I'll go back to the previous slide. Let's look at figure 2. So in figure 2, what we see is the separate two simulation model, this the annual simulation model and our simulation model. So we have the objective function, we have technical constraints, and we have the market clearance conditions. So this the objective function constraints are written in, or we write KKT conditions based on this objective functions and constraints, and we create a square system of equations. So it's called the mixed complementarity problem. So we have the complementarity conditions and the constraints which can formulate the mixed complementarity problem. And so we solve this mixed complementarity problem using path solvers in Python. And as a result of this path solver, we obtain the annual generation profile or the annual quantum of generation from each technology and the optimal investment strategy. And this output will be used to or we use this output to run the power flow and gas flow analysis, and to we simulate the hourly operation of the network. So coming to the objective function, again, we have the equation 1 shows the objective function with the, we have the revenue from operations from various technologies. So we can see that RT is the variable which shows the revenue, which is the revenue from the generation from various technologies. So each technologies can be a vector itself, in the sense the technologies which fall into that specific category and its generation comes into this variable. So this mathematical model can be a bit complex. So this is a simple model for the test network, which I'll be explaining later. But for a nationwide network, there can be all the technologies such as hydro or nuclear, etc., can come here. So in the objective function, we consider the revenue, the cost of operation of the network, and the carbon cost. Then comes the fixed cost of operations. So we get the profit as an annual cash flow, which is subtracted by the net investment outlay. So we have standard financial formulas to calculate the annuity factor. The fixed cost, FC is the fixed cost. So that can be calculated using the given formula. So it is quite simple formula. We calculate the using a specific capacity cost and the initial capacity. We calculate what will be the fixed cost, or we have assumed that the cost is a fraction of the total investment cost, and we have the net investment outlay for. So what net investment outlay is the actual payments for capacities reduced by the discounted residual value. So right now we have only 3 terms here because this at present we have done a simple calculation to see how a system with the wind, coal, and hydrogen can perform with the intention to expand further. So if we have data for expansion of other technologies, such as if we have hydro here, then one similar term or a similar term can be added for hydro here. So then the mathematical complexity will increase. So that's the objective function. Right now we have the constraints. So what we see here is these are the constraints for the test network, what I have shown here. So here we have the wind, coal, and CCGT, power to gas, etc. So for each and every component, we have the investment constraint and the technical constraint. And inside the bracket, what it's shown is the shadow price. So in general, how we so this is the front end of the code. In sense, when we write the paper, we will see this set of codes. But in Python, when we program this, we have the KKT condition, which is the we differentiate the objective function with respect to the independent variable. So ultimately, what we will be seeing is the square system of equation. That means the number of equation will match to the number of unknowns. So we will get answers for the Q. Q is the unknown value here, and I is the unknown value here. But K is the capacity of the technology. So let me show you a simple mathematical simple table which shows the this test network results. So what we can see here is these all are in kilowatt hour terms, but because we do this calculation in terms of kilowatt hours. So we have depending on the electricity demand and gas demand, we have the right proportion of the generation and right proportion of additional investments, and we have formulated the interaction between the gas network and the electricity network. That means for example, the wind generation should be there should be additional wind generation to meet the hydrogen production, and the hydrogen production would in turn would be used for the heating demand in the gas network as well. So this kind of interaction is simulated here, and this so this is the annual investment and annual production values. So this will be used in the hourly simulation model to actually find out the hourly operational scenario as well. So the next step in our research will be to perform this hourly analysis. So in order to perform this hourly analysis, we have tried to simulate, or we have tried to formulate 3 scenarios based on the published data from National Grid's Future Energy Scenario and Climate Change Committee 6th Carbon Budget. So these scenarios will differentiate each other based on the carbon price projections, carbon emission reduction target, whether the hydrogen is produced based on blue hydrogen or green hydrogen, or the nationwide carbon emission reduction projections, etc. So the overall, to conclude, I would say the research would bring more insights and policy insights into the future evolution of the Britain's energy network, and the right pathway, or which direction we should show. Should we go with more blue hydrogen, or should we go with more green hydrogen, and which would be the most cost-effective way? Would be some insights will be provided in that regard. And we will be using representative load curve. So the computational complexity will increase if we decide to go with every day's hourly load projections and generation profiles. So we'll be going with the representative values to reduce the computational complexity. So, and in future, the work can be extended to regional studies as well. Thank you.
Thank you very much. And I understand, I think this work also is being presented as a poster tomorrow in the session. I think it's 10 till 11 AM. So on to our third presentation. Mansoura, do you want to introduce yourself and do the presentation?
Do you see my screen? Okay, thank you very much. Hello, everybody, and welcome to my presentation here. So I'm Mansour Zangiobadi. I am a researcher in Newcastle University, and in the CESI session in this showcase, I wanted to share with you the energy lab, facilities that we have in the urban science building. Will be probably people who will visit on the Friday, and you will see in the background that is the energy lab that actually I'm sitting here. So I was the lead, lab demonstration activities in the energy lab. And the project I work with them, it was mainly about the mobility and EV and railway, and probably it's interesting, for you, especially in the railway side, to see how we can integrate EV and railway together to reach, smart mobility solution. Okay, so if we look at transport in general, in 2017, so I don't have new data, but 24% of the CO2 is from just only transport. So if we want to reach to the net zero emissions, so transport play a very major role here. And energy efficiency of transport is very important. We look at it. So in this figure, you will see here about the passenger and freight and how is the CO2 emission of different, transport. Mainly on the passenger is road playing the main, but on the freight is a bit different. So still is the road, but on passengers air is, a huge part here. But my work is mainly about the rail and road together through the integrated solution. And when we are looking at the integrated solution, and with the digital the world at the moment that we have, so we need to use this data in a very smart way, based on the infrastructure that we have on the energy, to communicate the data and to find the way, for example, for the train scheduling, for the road also, and do some decision making to make the transport more efficient and to decrease the CO2 in this way. So what we are looking at, on the mobility, it's an integrated solution, and it should be smart. So we need to use, in a very smart way of the data. For example, the train scheduling is very important in terms of regeneration and to use this energy for the feeding the other train on the other side, on the other track side. So it's very important. So using this data in a smart way will help us to reduce the CO2. So to implement this solution, and challenges we are facing in the forward, 3 themes are considered here. So it should be attractive for the passenger and consumer who are using the transport. For example, it should be integrated door-to-door mobility that, to attract them to use the solutions that we are proposing. Also, it needs to be affordable in terms of resiliency and flexibility, and also affordable to all the customers. And also looking at the sustainable, which main important thing is energy efficiency and using decarbonized mobility like EVs. If we look at all these 3 themes, we will see that the rail sector actually, the backbone of integrated mobility. So it's like metros all over the cities. It's like rail, between the different cities. So it is a backbone of the transport. So we need to look at that, how to integrate it with the road as well. One of the, electromobility state of that we are looking and, studied in our research, it's in 2 areas. One is the park and ride solution. So it means that, we avoid the construction of new car park in the urban area, and we alleviated, traffic congestion by, smart data that we have. And we, recovery of the, transport, we will see that how we do in the railway stuff, and also to be sustainable from, suitable and sustainable from both parties in terms of park and ride. It mainly means that instead of, passengers coming to the main city, they have, a place that to park their cars, and they can use the, rail for the commuting. And if we integrate actually railway for the what the EV charging station, it will be, no emission at all. So it is like railway is feeding the electrical, charging electrical vehicles, and also the passenger using in the park ride solution. So this is the, what is the state of the electromobility. I'm just hearing, about that when we are coming with a solution, we need to understand, how market propose, how it will be market take it. So if you look at the railway, we will have, different, metro, trains also. So we have their power flow and economic flow is shown in this picture. So the power flow is usually from the power plant through the transmission distribution network. It means that from the electrical network to the railway. It is from the railway also to the electrical network, some, regeneration back to the system. And we have the economic flow that could be, directly with the DSO or TSO, or could be through the energy suppliers. So all of this that you can see in this picture, elements here, are stakeholders of the smart mobility framework that we are, it proposed for future. So in terms of stakeholders, we have railway operator, train operator companies. It is, infrastructure manager in the railway. We have the energy suppliers that we see in the previous pictures that, distributing energy between railway and the grid. We have grid owners and the electricity market operator, customer of railway, and EV owner. So the smart mobility solution need to consider the views of these all stakeholders, and to find, somehow with the targets they are, proposing to be reliable, to be combinable, to be accessible, to be eco-friendly, to be economical. And in our project, we had, the stakeholders especially from the railway side, that they were very keen to play, their role on the smart mobility in future. So from point of our project, something is about, the simulation work and, the concept that we are going to explore. And the other part is the implementation in them in the practice, and, to validate, to test them, and to see that, when you come to the practical phase, you will see how many challenges that you never will be realized on the simulation part. So I work, on the energy lab that you see here in this picture. So in this energy lab, I'm just sharing with you which facilities that we have here. Here we have the bidirectional DC supply that I will explain you in more detail here. We have the power converter here, AC and DC, that's sharing a DC link and then exchanging the energy with the grid. We have the DC capacitors here. And we have, as you see in this picture, we have the battery testing facilities in the energy lab in the background, as you can see here. There are some projects running in the on the second-hand batteries for the cell module, and we are able to do in the rack module as well. So it is a summary that, you know, the facilities that we have in this energy lab here. And if you want to explain you in more detail, I will do at the end if you have any question on that part. So how it will run, you know, the facilities. We have, you know, the GUIs that usually they are on through the MATLAB integrated. So we can implement the model on the MATLAB on the GUI side, and then we will execute it. We go to the real-time target that we have here, and will be executed through the power converter. We have from, you know, 5 to 90, and in this lab we have 3 of 30 this tri-phase DC-DC converter, and then when it's executed, then through the I/O, you know, signals will be back and will be demonstrated through the HMI and lab view. So how is, you know, the lab and the facilities that we have here works? I particularly work on the not our, you know, facilities, but using, you know, our lab DC. Sorry about that. Bidirectional DC power supply, and integrated this facility with the test bed equipment from the industry. So what does this bidirectional power DC power supply do? You can model through it, you know, like EV battery emulation. You can do through the software that implemented inside this one, that actually this is this equipment here. You can do the PV emulation, and you can do also the battery testing through the bat control software. There are, you know, four of single devices, that each single device is 500 volt, 80 amps, 32 kilowatt. And if we, you know, make the matrix configuration of them 4 devices, we could reach, you know, 1000 volt and 128 kilowatt. And for a project that I did on the EV emulator, we used, you know, 3 in parallel. So we have a 500 and about, you know, 100 kilowatt, like a fast charging, you know, station. And as you see, this power converter here work as like, you know, feeding and regenerative mode. So you can, you know, inject the power to the grid or back. So like for the EVs we use in regeneration mode. So the 2 projects, I will go a little bit in more detail. One of them is what Smart Hub. And in the Smart Hub, we were looking at the integration of the battery, real battery, and EV and PV through DC regulated bus. If you look at the demonstration of the project here, we have the industrial partner, the turbo power system. They have, you know, provided for us the EV DC-DC converter and the feedback of this energy to the grid, AC-DC. And the smart power, you know, system, SPS, they have the battery, real battery, and also the energy management of a you know, whole system. And we in Newcastle provided our grid connection, which is a physical grid connection, you know, connected to the Northern Power Grid, and the EV emulator and PV emulator. But what we were looking at, you know, this project, we were looking at the DC bus here, because all of them are, the output is DC, and instead of, you know, for example, PV go to the AC and back to the DC again, we were actually, you know, looking at the missed opportunity and share infrastructure in the DC link. So energy can be dispatched through the DC link between the battery, between the EV, and between the PV. So this is the demonstration of project in our lab. So this is the TPS converter, that it was grid-tied inverter, and the DC converter for the EV charging inside this black box. This is the real battery through the SPS company. So the DC-DC converter to connect to the DC link of the this black box from TPS, and we had the EV emulator and the PV emulator, as I show you, in previous slide, and they were connected to the grid. The real battery by SPS was a 50 kilowatt battery. So, and the battery current, charge advice was, in this figure, and it was like, a 1C batteries. So for the project, emulator, which we used the GSS Regatron, we actually modeled the Nissan Leaf battery with this parameter inside the BatSim software. So this is the software for our emulator that emulate the EV behavior on this one here, on the GUI of that one, and then we just tested it, and we can see you here that is a cycle of the battery charge and discharge, exactly like a real battery. So if you like a real battery, the cycling of the battery, discharge and discharge, is very similar to this one. So actually the emulation of the battery is very close to reality, and you will see here is like, the discharge side here when the sign is like that. And we look on the EV emulation from the 20% to 80% of the charging that usually used for the batteries is maximum the 80. So we tested with the charger, the TPS one, which was 100 kilowatt, 200 volt, 50 volt. The DC converter for the EV charging, and you can see that the fully of charge of the battery from the 20% to the 80% have been shown here, and we tested it, as you can see here, is like 200 amps. But this figure is for when we was demonstrating 190 amps, and you will see that this sign here shows that the EV is charging started from around 10%. And then we also,
sorry, we are running out of time a little bit. It's really interesting. I just wondered if you might be able to summarize the remaining slides for us, and then we can move on to Q&A. Thanks.
So we use the emulator again for the PV, emulation, and this is the result that we got when we have like a CHAdeMO 50 kilowatt. We wanted to charge the EV, and we charge it just from the battery and PV on the DC link, and nothing from the grid. So I will move to the other, because I will just explain the other one. It was about the grid and rail solution. So what we were looking here, the solution, it was, the railway, the DC railway, which is one-sided, and we have the rail converter, grid inverter, and battery here, converter here. And we want to, what's happening here, we want to capture the braking energy that is wasted on the DC network, because it can't go through the rectifier here, to capture it in the energy storage and release it to the gradually to the LV grid. So we are building a soft open point with the battery storage, integration of the railway metro to the LV grid. So here, this is demonstrated in our lab, the equipment, and this is the result we got here. So this is how we model, emulated the rail behavior or our emulator here. Again, the same, and you will see this sorry, this is the braking energy that we are going to capture, these spikes here. So these are the braking energy when is the voltage is more than threshold, it will activate the rail converter, and the energy will be captured. So it can be stored in the energy storage, or it can be, released to the grid. So if we look at the, the battery EV charging station, and we gather the data from this charging station next to the USB, and when we look at the solution, we could see that from the braking energy, we could capture in 2 lines of metro base of experiment this amount of energy, and this can be charged, 200 EV batteries in a day with a Nissan battery that is 40 kilowatt hour. So I just quick here. So this is the our research has been published in different journal and conference paper, and you're interested, you can look at them. Yeah, thank you very much. I hope you enjoy, and I'm sorry for the long presentation.
Thank you very much, Mansouri. That was really interesting. So moving quickly on in the last 3 minutes or so that we have left to some questions. There's just been one in the chat there from Ken McKinnon for Akhil, asking him how many players were used in the game theory approach, and any differences between the core knot solutions, and how different that would be with the core knot solution compared to a centrally optimized system. Akhil, I know you've already answered this, so I just wanted to give the opportunity for you to answer that yourself. And Ken, if you have any further question there, or indeed anybody else, if you can use the reactions, put a hands up or something, and I will get to you for any questions. Thank you.
Sure, thanks. I'll take two more minutes to explain further. So here the number of players depends on our ability to perform the optimal power flow and gas flow. That means we have a publication where they have performed the nationwide transmission networks, optimal power flow and gas flow. So what we are doing is we are taking the same data here. So we have 54 electrical generators there. So we can assume that we have 54 players in the game. For the electricity network. For gas, we have depending on the node, we have to see. I think there are 70 nodes. Yeah, so that would be the number of players, around 100 plus. And yeah, there's the Carnot solutions. So it is assumed to give the global optimal solutions for the perfect competition model. So here what we see is that we are formulating a liberalized energy market, which is the essential characteristics is that we should have a perfect competition model, and the Carnot oligopoly model is the perfect competition model, which is solved using the mixed complementarity problem. So for a small network, the solution for a centralized optimal problem, for example, if we use a linear programming method, that could be same. But we have to see how, for a complex network, how the solution would look like. So we'll have to look more into that. Thank you.
Thank you. Is that okay there, Ken?
Yeah, so the 56 generators were at different locations in the network, were they? And so they weren't in direct competition, or?
Yeah. So that it's in different network. I mean, like we have the network topology. So how far the networks are placed. So we need the network data in terms of like what is the cable used, or what is the length of the cable. So that should be used to simulate or that is essentially used to perform the optimal power flow. But the idea is when you do the optimal power flow for entire given year, and the annual generation should match with the investment models solution.
Okay.
I hope I answered.
Thank you. And I think we've got a question from Rhiannon as well.
Yes, quickly, as long as people don't mind, because I'm just conscious of time. This was just for Dave, because I started CESI before quite a lot of after quite a lot of the research, and it was just a question that relates to your India work. I just wondered if there were any interesting links from your community work that you've done in other regions and how that compares to India.
Yeah, so we did some work on the CESI project, which was a different project. And we had case studies in India where we were trying to do something similar with modeling communities and understanding their energy demand. One of the big differences in India is that you're not necessarily looking to reduce demand, but you're maybe trying to stop it increasing by as much as what it is going to, because there's a rise in cooling load in particular. And so a lot of our conversations in India were based around rising cooling loads. What big difference with our work in India is that we actually had co-production workshops with householders themselves. So we were able to understand their energy behavior a little bit more, the cultural impacts of that, and also the kind of things they might be interested in doing to change their demand characteristics. So we didn't do that within CESI for the UK case studies. We've done that in India. And what that shows is, first of all, in the case of India, as much as anywhere else, India is huge, very diverse, very complex. And you have to understand that as I was talking about the importance of tailoring a model on a specific community, that's even more important in India, because what might happen with a community in the south of the country is completely different to the north of the country, very different kind of regional cultures and income breakdown and so on, and housing stock. So the kind of common learning across all this work is the kind of parameters you need to try to capture in the model when you want to genuinely tailor your model towards a community, but also an acceptance that there's lots of really quite interesting but quite complex things that go on in these communities that you only really get to the bottom of if you actually speak to householders and have that kind of interaction. So this idea of kind of co-production, which is kind of anathema to a modeler that just wants to use numbers, just wants to stick numbers into a model and get some numbers out. But the idea of actually understanding the context of that by speaking to the people who you think you're modeling. Generally, these models are not really modeling people at all. But so that's the kind of common ground. But yeah, as you switch from one part of the world to another part of the world, obviously there's the heating versus cooling switch, but it's actually more complicated than that in terms of the technologies that you imagine might penetrate into that community and therefore needs to be accounted for in your model.
Fantastic, really interesting stuff. So unless anybody's got a burning question, if I could suggest that they get in touch. I think the contact details are quite easily accessible, so you can contact the speakers after this event, but we have run out of time now. So I want to thank you all very much indeed for your participation in this, and thank you especially to our 3 fantastic speakers, and enjoy the rest of the programme.
Thank you all.
Thank you.